All right. All right, so let's get this started. The next Elixir version will likely have the first release candidate this month of the beginning of next month is going to be Elixir 1.19. So today we're going to talk about compile time improvements, type system updates, and interoperability, which I'll say just interop for the rest of the talk, because life's too short to spell it the whole way every time. All right, so compile time improvements. So the short version is that Elixir 1.19 can yield up to 4 times faster build times on large projects, okay, which is massive. So in order to understand, but emphasis on large projects, we're going to get to there soon. Previous releases, so in order to us to understand what is happening here, right? So what do we do before? So in Elixir, since the beginning, I think like one of the first blog posts on the Elixir website is talking about the parallel compiler. So files in a project were always compiled in parallel. So if you have 100 files, we'll compile those files in parallel, right? And in an ideal world, right, so if you're compiling everything in parallel, if you're doing something in a machine with 10 cores, and then you migrate to a machine with 20 cores, everything should be twice faster, right? But in real life, we have bottlenecks. We have things that cannot be fully parallelizable. And one of those things that are a bottleneck is the code server in Erlang. So every time you need to invoke a module, if that module, like you're calling string, if that module is loaded, it's going to be quick. It's already loaded, right? We just call the function, super quick. But if that module is not loaded, then it's going to call the code server. The code server is going to be like, okay, I have all those applications here, all those directories. Let me see if one of them defines the string module. And then you have to load that module, right? So the code server is a bottleneck, which means that we cannot get the 100% CPU utilization. And over the last like 2-3 years, I'm speaking about new Elixir releases, and we have been constantly improving compilation times, right? So sometimes I would come say, oh, it's 15% faster. Boot times now are 30% faster. And usually when I'm talking about those things, is because we have been improving the code server. We have been sending pull requests upstream. So for example, one of the things that we did is to cache file system lookups. Every time we would try to find a module, right, we have to go through the file system, through each directory, and say, hey, do you have this module? But now we cache the files in the module, so we don't have to query the file system every time. We are not removing the bottleneck, but by making the operation much faster, the impact of the bottleneck is reduced. Right? So we started caching file system lookups, and we started decentralizing work. So now you're like, hey, before you were like, hey, where's the string module? The code server would look for the file, right? It would read the file, load the file, and then finalize it. And now you're like, oh, just tell me where the file is, and other part of the code is going to read it, is going to start loading it. So we are like making things faster, decentralizing work, and that was most of the improvements in previous releases, all right? In Elixir 1.19, we make 2 improvements here. So the first one is that compile modules are now lazy loaded, okay? And this yields up to twice faster compilation time. So what is the idea here? When you define a module in Elixir, like def module, blah, 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 right? You define a module. At the end of that is the module definition, we already went and loaded that module, right? So that's work for the code server, right? We already went and loaded that module. And they were like, well, what if we just don't load it? Like, so we're always loading it, even if it was not used anywhere else during compilation times. So like, well, what if we just don't load it? And then if somebody else needs this module, then we load it, right? It's like, it's such a simple idea. It's one of those ideas that you're like, hey, you know, we could have had this idea 10 years ago. It just, that We didn't. But at least now we have for the next 10 years at least, right? So there's that. And the idea came, huge thank you to Alex from Remote, because he was the one who was profiling, benchmarking compilation times. I was like, hey, it seems there is still a lot of time spent on loading modules on the code server, which led to this fix. And the other one, oops, fat finger, I'm sorry. The other one is that we introduce a new environment variable, very easy to memorize. That should have been the trivia, James. What is, after the keynote, what is the name of the variable to parallelize the compilation of dependencies? It's mixOS deps compile partition count, right? And the idea here, again, in an ideal world, like, so Elixir compile dependencies one by one, right? So in an ideal world, we should be able to use 100% of the CPU as we compile each dependency, because we compile all files in parallel, right? But we know this ideal world does not exist. And then furthermore, when we are talking about dependencies, there are some like pathological cases. Maybe you are compiling a dependency that compiles native dependencies, and that native dependency is not compiled in parallel. So it's time your CPU is not going to be fully utilized, right? Or maybe that dependency needs to download something. So when we are compiling dependencies, more things can happen, and when those additional things are happening, it can reduce the amount of cores being used. So we introduce this environment variable, and you just set it, and now you're going to compile your dependencies in parallel. And a huge thanks to Liam for the initial proof of concept behind this idea. And those are and when it comes like to the second one, mixOS deps compile partition count, both of them actually, the improvements that you get is going to depend a lot on how many cores you have on your machine, because the more cores you have, the more impactful a bottleneck is going to be, and the larger your project is, the amount of dependencies your project have. So just an example, when I'm running Livebook on your machine, the first change did not make anything faster, because Livebook compiles like in 6 seconds, 7 seconds on my machine. But there are people where their projects take like 7 minutes to compile, and now takes 3 minutes and a half, right? And for dependencies, I constantly see a 2 times improvement on my machine, but some people are reporting up to 4 times improvement. So it's going to depend. And a good value for the mixOS deps compile partition count is like half of the number of the cores on your machine. After more than half, we don't really see an improvement, because again, we're trying to use the cores the best that you can. So Elixir by default is going to use maybe, I don't know, 60%, 70% of your cores. So we just need to do a little bit more additional work to get that 100% CPU utilization. So that's the idea, right? So now we are doing less work doing compilation. Compile modules are less loaded. This means it's less work, so it's faster, and we are relying less on the code server, so the bottleneck is going to impact us less. And now you can parallelize how your dependencies are compiled, and that can lead to large improvement as well. Second topic on the agenda, type system updates. So a quick recap, we have been researching and developing a type system for Elixir. Guillaume, he presented earlier today with Giuseppe Castagna and myself. We've published a paper, we've published a bunch of blog posts on the Elixir website. And a quick recap, in Elixir 1.17, it was the first release with type system features. So we supported basic types like integers, floats, speeds. We supported atoms. And we supported composite types like binaries and maps. But back then, or still today, we only support maps with atom keys. If we put something else than an atom key in a map, then we just say, oh, it's a map, but we don't know what is inside. So we can only track atom keys inside, right? And yeah, so we released these. And when we released these, we started finding bugs in your application. Guillaume went into the kind of bugs we would find in his presentation earlier today. So if you missed it, you can watch it online. Right, so this is just a quick recap. And then Elixir 1.18, which is the current release, we added support for lists and tuples. So we are working on the foundation. We are making the type system smarter so we can find more bugs for us. and it can understand more of the Elixir programming language. The more it understands of Elixir, the more capable it's going to be to find bugs. So added support for lists and tuples. Also, we added type inference of patterns. So now if in a pattern you are doing pattern matching and you say X equals a list, we understand that X is a list, we pass that information forward. We started type checking local and remote function calls. And even if you define an invalid pattern, imagine in a pattern you say, oh, X is equal a list, and in the same pattern you said X equal a map, that would never be true. We started detecting those. We are finding bugs, right? We're trying to find more bugs, like to say, for free, right? We're not changing any of our Elixir code yet, right? We just upgrade the Elixir version, and the type checker is updated, and it's finding more bugs. And in Elixir 1.19, the features that are coming is support of maps of any keys. So I said before, we could only track atom keys in maps, but now we will be able, there's a pull request from Guillaume, we'll be able to track any key in the map. We also support anonymous functions, so as you pass anonymous functions around, we'll be able to understand what they are doing. And we support type checking of protocols and implementations. And I'm going to show some examples soon, but it's very interesting because we are still doing work on the foundation to make sure that the foundation is good so we can continue adding more things on top. So for example, in order to support anonymous functions, one of the things that are new in the theory of the Elixir type system is how we do gradual typing. It's a novel approach. It was developed, it's new, developed with Elixir in mind. It can be applicable to other places. But when you have a new theory, when you have to implement that, then you need a new implementation, right? So there is not something that we can get and use. So supporting anonymous functions requires like more research to implement it and develop it. When it comes to type checking of protocols and implementations, the way the Elixir compiler worked is that we would compile code, then we would type check, and then we would like compile your protocols. But because now we want to type check the protocols, we have like to do a reasonable rewrite of the compiler. So we compile code, compile protocols, and then we do type checking. So that's what we have been working with. And just to give an example of what you'll be able, which kind of warning, right? Which kind of bug we'll be able to find now in Elixir 1.19. So imagine this code, which is clearly, maybe not so clearly, but that's invalid code. So what we do is that we have a function hello that receives a range as argument, and it's interpolating that range. But range, you cannot convert it to a string, right? Like you could pass a PID there. You cannot convert a PID to a string, right? So if you do that interpolation and you executed that code, you would get a runtime error. But now with Elixir 1.19, you get a proper type violation. I don't know if you can read it, but it's basically saying, look, you are passing a range to a string interpolation. We do not support ranges in string interpolation. We do support dates, datetime, atom, binaries, at least everything it supports, everything it was expecting, right? But it's now telling you at compilation time, at compile time, before you run the code, that that thing is going to fail, right? So giving a step back here, when we were talking about the type system, I said when we announced that we are starting development, I broke down development in 3 major milestones, okay? The first one is type inference from patterns and guards. That's the one we are right now. And the idea that I said is, look, we are going to add a type system to the language, and we are going to look at your code, and we are going to find bugs without you having to change a single line of code. It's finding bugs for free, right? That's the goal. And then we can work on the error messages, we can work on performance, make sure the type system is faster, right? Is fast. And then if we are happy with those results, then we would go to milestone 2, type definitions and type structs, right? So you would be able to type a struct and say, hey, the field in this struct is a binary, and this one is an integer, and this one is a user, right? So that's the second part of the milestone. And then we have the third part, which would be effectively typing functions, behaviors, and protocols. So we are, as I said, we are still on the first milestone. And if we think about everything we had to do, so we need to do precise support for all data types, that's done. type checking of all language constructs done as well, type inference of patterns, and the only thing missing is type inference of guards, which is something that I actually wanted to add in Elixir 1.19. If you see my previous presentation, I'm saying, hey, in 1.19, we are going to have type inference of guards. But as you can see, we don't have it yet. So what has happened? Well, something that never happens in software projects, which is a slight change of scope. So we went from, instead of having type inference for patterns and guards, what if we have type inference of all language constructs? And in order to understand exactly what this means, what is the impact of this change, I'm going to go through some code, okay? So let's talk about type inference. So no type inference, that's the world we have been living for quite some time, right? So there is no type system, so there was no type inference as consequence. So imagine this very simple, very silly code, add strings, receives two variables, two arguments, A and B. It calls string to integer passing A. So it's going to convert the string to an integer, so X is an integer. Then calls string to integer passing B, returns Y, and then we do X plus Y. If you have no type inference, the only thing we know about this code is that, well, it receives, which I have here on the bottom, is that it receives a dynamic argument, which means, oh, we don't know what is the type at compile time. We only know the type at runtime, when we run the program. So the first argument is dynamic, the second argument is dynamic, and we return something that is dynamic, okay? So this would be no type inference. Something that we have in Elixir type system, and most type systems have, is something called local type inference, which is kind of thinking that we can infer the types of variables. So many typed languages, you don't have to put the type in a variable, right? You just say let X or whatever, and then the type system figures out what is the type of X for you. That's local type inference. So if we have local type inference, we wouldn't know that what A is, we wouldn't know what B is, but we would know that string to integer only returns an integer. Therefore, X is an integer. Therefore, Y is an integer. And therefore, X plus Y, it's receiving two integers, and therefore returns an integer. So now it's a little bit better, right? Because we use type inference, we were able to get a little bit more type information that we can put on this function. And now if anybody calls this function and does not treat the argument as an integer, treats the argument as something else, we would get a typing violation. So being able to infer types is good because it will help find bugs in other places of the code base. So that's local type inference. It's already better. We are no longer saying that the return type is dynamic. It's an integer. And what we wanted to work on, and we will still, is type inference from guards. So if you say, look, if I have an add strings and I say that this function only works when A is a binary, then B is a binary, which is a string, right? Strings in Elixir, they are UTF-8 encoded binaries. They are binaries. So if you added this guard, then we would infer that the type is binary. It receives a binary, receives another binary, and returns an integer, right? So that's good. More type information. But you can be thinking, but José, isn't this like kind of redundant? Because yes, I can add the guards, and adding guards is useful in a lot of situations. But in this case, I'm calling string to integer, and string to integer can only receive a string, a binary as argument. Couldn't the type system like figure that out? And that's exactly the goal. That's why we want to have type inference from all constructs. I want to be able to look at this and say, look, because I'm passing A to a string to integer, and a string to integer only accepts a string which is a binary, I know that A is a binary, right? So we want to look at the program, at all the variables are going in, going out, look at all the constructs, and get that type information, right? So this is meant to be good. It's really good news, right? So that's what we are aiming for now. So we changed the scope. However, right, so this is good. However, there are always trade-offs, right? And type inference comes with some costs. that is important to talk about, right? I have trying to be, since the beginning, when working on types, like we're not going to be driven fully by hype, right? We're going to look at everything, we're going to evaluate the trade-offs, and we're going to reason about those things in a way that makes sense for us, right? As developers, as a community. And when it comes to type inference, some of the trade-offs can be speed. Usually type inference algorithms, they can be more expensive than type checking, right? So things are going to take longer. It comes with expressiveness. So if you're building a new programming language, it's not the case for Elixir, but if you're building a new programming language and you want to say all the features in the language, they need to support type inference. Usually, in typing theory, the amount of features in the language that you can type infer, it's a subset of the features that you can type check. So languages that say, oh, everything has a type inference, the amount of constructs they can add end up being limited. This is not a problem for Elixir because we can always say, oh, it's dynamic, right? We can always fall back to dynamic. But it can limit expressiveness. It can also affect errors because imagine that you have A calling B, calling C, 3 different functions, okay, in different modules. If we infer the type for C, and then we use that to infer the type for B, and then there is a typing violation in A, now you're having a typing violation in A caused by C, right? And so you have to understand why C got to that type signature, and why that impacted B, and how that impacted A, right? So it can make errors hard to understand because the signatures, they are being inferred, all right? So that's a potential downside. And it can also impact incremental compilation because again, imagine A calling B, calling C. If you infer the type for C, if C changes, you have to infer a new type signature, which means you have to infer a new type signature for B, which means you have to infer a new type signature for A. So now you do a small change in your code base, and you have to like do a bunch of inference, and maybe recompile some modules, and that's not good. That's why some people who work on some other type of programming languages, compilation times are high. They're like, oh, just add some type signatures and it's going to get better, right? That's a common advice. It's exactly because of that, to decrease the impact of changes in the code base. So with all this in mind, it's like, are we sure we want type inference, okay? Do we want that? How is that actually going to impact us, right? So we heard about the upsides. Those are some of the downsides. So how are we doing this in Elixir? And in Elixir, the way we are tackling this is that we are decoupling inference from checking. We are decoupling type inference from type checking. I'll try to be very brief here, okay? So what we do is that we perform type inference with your dependencies. So when we do type inference, we're only going to look at the code from your dependencies. And why is that? Because your dependencies rarely change. So we don't have to do a lot of rework when your we have to do rework when your dependencies change, but because your dependencies change rarely, we're not doing that work all the time. And then we perform type checking with the whole code. Let's break this down, okay? So we are back to that same function as before. I just did one tiny change. Can you see this in the back? All right. So I just did one tiny change. So we have add strings, receive A and B. It calls string to integer, which we know receives a binary, returns an integer. And it calls my app string to positive integer. It's very similar to string to integer, except that we also check that the number is greater than 0, right? So it also receives a string, a binary, and returns an integer. But we are checking that it's greater than 0. So if we have type inference, right, what is going to happen is we call string to integer passing A, and we know that string to integer expects a binary. Therefore, A is a binary. And then we know that string to integer returns an integer. Therefore, X is an integer. All right? Now, when it comes to B, my app string is defined within our application. A string is defined in Elixir. It's defined in your dependency. But my app string is defined in your application. In this case, remember what I said. Type inference only considers the code in your dependencies. So in this case, because you are passing B to something from my project, it's as if it doesn't exist. So we're like, okay, so B is dynamic. We don't know how it's being used. Y is dynamic. Therefore, I'm calling the plus operator, the addition operation, passing an integer, which is x, and y, which is dynamic. We don't know what it is, but we know that plus only accepts integers or float. So we get to the conclusion that that is going to be or integer or float, and then we get to this type. So we receive a binary, which we could infer. B, we cannot infer it, right? And then it's going to return something that is either an integer or float. So this is not as precise as the full type, right? That we could have, that from binary to integer is not as precise as that. But it gets a good amount of information about the program that we can use to type check the rest of your code and find bugs in the rest of your code. Right? And when we do type checking, then type checking considers all the information. So type checking is going to be like, okay, A is a binary because I'm passing it to a function that expects a binary. X is integer. B is going to be a binary because I'm passing it to a function that expects a binary because we did type inference for my app string, so now we know how it works, right? So therefore, Y is an integer. So when we do the type checking, we get back the correct type. It's just that we don't write it to disk, because if we wrote it to disk, whenever my app string changed, we would have to type check this code and do a type inference again. So the idea is, okay, when your dependency changes, we apply type inference on direct callers. So if your module calls Acto, right? If you update Acto, any module that directly calls Acto need to be type inferred again, right? But just that time, just when you change the dependency. And just the direct callers, that thing, oh, this thing calls this, calls this, calls this. No, the chain is no longer there. That's the important one, right? We don't have, oh, when this thing changes, it's going to change this thing that changes this other thing. No, we're not doing that. So when your dependency changes, we do the inference on direct callers. And when your project changes, we apply type checking on direct callers. So we don't have, like, this incremental compilation is fully preserved. Okay, so that's the idea. That's what we have been working on. And here's the thing. It's a lot of words, but what it means, like the important slide, the thing that you have to care about is this. We want to find bugs for free and fast, okay? And what I'm saying is type inference. We're only going to use type inference if there are no type signatures. In the future, you're like, José, I don't like this. I don't want to rely on type inference. In the future, you'll be able to write your type signatures. And when you write your type signatures, everything that I talk about does not matter, does not come into play, right? So again, the idea is we have a lot of existing code today. How can we look at this code and find bugs for free and fast? That's why we're talking about all of this, right? And this is already main, this is already implemented, except for guards, okay? So it's something that you can already try out. You're going to have false positives, okay? You're going to have like warnings that are not really warnings. It's work in progress, but a lot of the work is there, right? And to recap, you actually don't need to know any of the previous slides, right? I am explaining how it works, so, you know, buzz factor, trying to reduce it by a factor of 500 here, right? But when you're using a type system, you don't have to care about that, right? The only thing you need to care is find bugs for free and fast. And if you have type signatures, it doesn't matter. So to wrap this up, this work is a partnership between the CNRS and Remote. And the development is sponsored by Fresha, Starfish, and Dashbit. So a huge thank you to those companies, because otherwise this work would not have been possible. All right, let me brief. Last topic, and this is going to be a quick one, so we can have time for some Q&A. Let's talk about interop. So I said that 2025 will be the year of interop for Elixir. Okay, and we already started seeing some like very interesting results. So earlier this year, Jonathan Kosko, he wrote this article on the Dashbit website, embedding Python in Elixir. It's fine, where he announced 2 libraries, Python X, which is effectively bringing the Python runtime into Elixir, into the Erlang virtual machine. And the rationale is, when we started the numerical Elixir effort, I was like, look, we're not going to depend on Python libraries. And nothing against Python, it's just that, look, if we want to build our own identity, if we want to have our own optimizations, our own libraries, if we want to leverage concurrency distribution, we need to have the flexibility to do so. And if we depend on another high-level library, that's going to constrain us. So now after all this time, it got to a point where we've built the foundation that we needed for numerical Elixir. And it's getting to a point where companies, they want to try Elixir for something for machine learning, but they can migrate initially 30% of their stack to Elixir. That's the initial idea, but they are still using Python for the other 70%. So we should have an easy way for them to plug into their existing infrastructure to bring some libraries from there. And that's the idea here, right? Like now we can embed Python into Elixir. We also released Fine, which is a library for better integration between Elixir and C++. In the keynote today, we had a great presentation from Mateus and David talking about Atom VM, bringing Elixir to microcontrollers, WASM, and the browser. And tomorrow, slight spoiler alert, we're going to hear more about Phoenix Sync and how we can approach integration and interop on the front end in different ways. Right? So when we're talking about language interop, right, we're talking about Python X, which is Elixir and Python. We're talking about Fine, which is Elixir and C++. Atom VM, bringing Elixir to microcontrollers. WASM, Popcorn, bringing Elixir to the browser. Right? And it's not only about language interop. It is about web application interop as well. Right? And Phoenix LiveView was leading the space here when it came out, what, 5, 6 years ago? And the idea is, well, what if we integrate the client and the server, right? And LiveView has a very server-centric view of the world, right? So I'm really looking forward tomorrow about Phoenix Sync and say, hey, well, how can we integrate the client and the server together, preserving a more client-centric view of the world? Right? We also have projects like Inertia.js for Phoenix, again, exploring this web application interop. We had other presentations here today about Hologram and LiveView and many other projects around. And now that we are talking about types, maybe we can even think, what if we get the Elixir types and, I don't know, convert them to TypeScript types and send them to the front end to improve interop? Right? So I think there are so many exciting things happening with interop in the Elixir community right now that I thought it deserved being called out, right? And sometimes people come to me and they say, hey, José, what should the Elixir community be working on? And for me, it's those two slides, right? We should be working on interop. I know that we love our language. I know we love the Erlang virtual machine. I absolutely love the ability that I can kind of throw any problem at the Erlang virtual machine and it's going to do a great job at it. I can throw data processing, machine learning, embedded software, web applications, distributed systems, right? We can throw all those problems at them. It's going to do great at that and often do all those things at the same time, right? Which is really impressive. Right? But we have to remember that we are not alone, right? And sometimes somebody's going to come to us and say, hey, I want 30% of your stack. I want to use your stack for A and B, but when it comes to C, I have to use something else. It may be for a technical reason, maybe a business requirement, or maybe because they just think something else is better for that particular problem, right? And they should have good paths for doing that within our community too. Right, so that's all I had to share for today. Thank you very much. Is this the officially sponsored water of the event?
Yeah.
Did I get the right one?
It's official.
Yeah, all right.
All right, thank you. Let's give José another big round of applause. So you can ask questions, and you can ask questions on the app. So I'll have you guys take a few minutes to either ask or vote on which questions we can cover. And while you're doing that, are there any questions here in the room that you have? You want to come up and I'll give you the microphone.
Sure. So guards are not in yet, but how do you plan to handle like when the guard mismatches the infer type, or does the guard just override the infer type?
So a guard cannot really override the type. So what we do is that as we are going through the program, we are kind of collecting type information from the guards, from function calls. And then when they conflict, if at some point we get conflicting information, that becomes a type violation, and you're going to have a long text printed on your terminal or your editor. So we are basically, there is never really an overriding per se, we're just collecting everything, and if something contradicts, boom, it's a bug in your code, hopefully, not mine.
Okay, here's one. Oh, we just lost one. I'm going to ask it anyway. Do you think the type system will impact APIs of popular packages like Ecto?
Oh, that's an excellent question. I think, so I even opened maybe 1 or 2 months ago an issue in Elixir with some APIs that we will need to deprecate in Elixir, because as we add, so the short answer is I think yes, I think that's going to happen. I don't know still how much, what is the impact, but I think as we add the type system, we are going to see that some patterns, they are not really useful from the type system point of view anymore. So there's a long discussion in the Elixir issues tracker because Elixir 1.19 is deprecating the struct update syntax because it's just not an efficient way of doing that typing-wise. So that's going to happen, but I don't think anybody should worry right now. It's like, so far, I think Elixir has a large standard library, and I think so far we identified 2 functions or something like that. So, but I think we're going to see some things like, that was actually not a good design typing-wise, and we'll have to rethink a few of those.
Okay, these things are changing. What impact, if any, does the type system have on the development of the official LSP?
Oh, that's a good question. I think the folks working on Expert, the language server protocol, they are still, so no impact so far because, you know, like they still have to support Elixir 1.16, 1.17, because otherwise they will release a new LSP, and then if they just support latest Elixir, which is where those things are happening, then it will not be accessible to many. So they are focusing on other parts of the problem, but we are now constantly in touch, you know, about when I'm designing a new API in Elixir, I'm saying like, hey, would this be useful for you to the type system in the future? So short answer, there is definitely an impact, but it's not right now. It's going to be more medium, long term when we really think about putting all those things together.
Okay, you got your wizard hat and your crystal ball for this one. How far away is type declarations as part of the language?
Yeah, so what I was thinking, no promises. You should even not put this on the YouTube video. I'm kidding. But so my thinking would be that we would release typing of guards now, structs from 1.20, and depending on how everything went, like by this time next year, we would be having type signatures. That's what I was thinking originally. But no. Because you already saw that the typing of guards already got delayed, right? So these estimates, the estimate of what I was thinking of in a year from now, it's already invalid as of this presentation. So I would say like conservatively, it would be on, hold on, 19, 20, 21, 22, 22, which would be second semester of next year. But it may get delayed again, right? Because there are a lot of, we're still working, you know, we're implementing a whole type system, we're still working on the foundation, there is new theory, so there are things like generics. We haven't started working on this part of the type system yet, and it's going to be an important functionality for Elixir, because, well, like we have enum, right, that is working with lists of A, we don't know what A is, right? So there's a lot of work ahead. My very optimistic version would be in a year from now, but that's already not there. So maybe in 18 months, but potentially more. So yeah. But again, like, good news is we are working hard in finding bugs for free for now. That's the main message. And then for the ones you have to pay by writing code, writing type signatures, is going to come a little bit later.
Let's give him another round of applause, please.